This is a video explaining how to do exercise 7b question 4 from the OCR Cambridge Mathematics FP3 textbook. It's a question on further trigonometry, and in the words of the textbook, it's about using the formula in reverse. It's using the formula to turn a power of a trig function into a series of multiple angle trig functions, and which are much more amenable to integration. This one's a little unusual and potentially a little tricky because it's proving a 2n. It's not a particular value, and it's a relatively surprising little result here, very strangely simple result. Anyway, let's get on with proving this. So, as I said, it's about using the formula in reverse. So, first step is to change this cos to the power 2n theta into multiple angles, and we'll use the standard formula that we've learnt for this, which is to say that 2 cos theta to the power 2n is going to equal a series of groups of powers of z. So it's going to look like this. The first one with quantity 1 is z to the 2n plus 1 over z to the 2n plus 2nc1 z to the 2n minus 2 plus 1 over z to the 2n minus 2, because remember the powers are going down 2 at a time here, plus, we'll do one more, 2nc2 z to the 2n minus 4 plus 1 over z to the 2n minus 4, plus, and so on, down to, now, because this is an even power, there's going to be a constant term, and it'll be the number in the middle of the table, the Pascal's triangle. So it's going to be 2nn on its own, which is already quite reassuring because that's what we're looking for there. Now, we're going to use this expansion to do the integration. So, we mustn't forget, before we integrate, to divide by 2 to the power 2n. It's got to go to the other side. So our integral we can write now as the integral from 0 to pi by 2 cos to the 2n theta d theta is going to be 1 over 2 to the 2n multiplied by, now mustn't forget the 2's on this side as well, because remember z to the 2n plus 1 over z to the 2n is 2 lots of cos 2n theta. So there's in there 2 cos 2n theta. Plus, then we're going to end up with that 2nc1 there, 2nc1 2 cos 2n minus 2 theta, plus, and so on, finally ending with, again, our 2ncn there. Now, these are all now multiple angles, so we can integrate them to sines. And so this is going to, we're still integrating at this point. Right, so when we integrate these, we're going to get this expression here. It's going to equal 1 over 2 to the 2n. Now here, this first one is going to integrate, and I'm going to include the 2's at top and bottom so we know what's going on. I know they are going to cancel in a minute. So 2 sine, sorry, quick skip back past that. Hadn't noticed we'd gone off the bottom of the screen. So we ended up with this expression here, and I simply wrote that out down here as part of the integral and divided through by 2 to the 2n. I think we need to see more of this, don't we? I divided through by the 2 to the 2n to get an integral here. My integral 0 to pi by 2 cos to the 2n theta d theta. It's integral from 0 to pi by 2, 1 over 2 to the 2n, multiplied by all of this expression here, get down to there, d theta. Now, we're going to integrate this now. That's just a constant number in the front. These coses are going to integrate to sines, so 2 cos 2n theta integrates to 2 sine 2n theta over 2n. And the next one is going to integrate to 2n c1 2 sine 2n minus 2 theta over 2n minus 2, plus, and so on, until we get to this term here, 2n cn, which becomes 2n cn theta, 0 to pi by 2. Now, you might not be thinking that's too helpful at the moment, but notice what we've got. We've got even multiples of n here, all of these values, because 2n, 2n minus 2, going down in 2's all the way to no sign there at all. Even multiples of theta for pi by 2, theta equals pi by 2. So, because they're all even, an even multiple of pi by 2, the sign of that is 0. So I'm just going to write that in. So sine of even multiples of theta for theta equals pi by 2 are 0. And of course later sine of 0 is 0. So this simplifies drastically. That becomes 0, that becomes 0, and so on, all the way down to this term here. It's the only non-zero term here. So in fact this becomes 1 over 2 to the 2n times, and that'll be 0 in the second one, 2n cn pi by 2. And that of course simplifies to pi over 2 to the 2n plus 1 2n cn, which is what we wanted to show. And that's how you do that problem.